Okay, now let's get started. Hi, everyone. I hope you are all doing great. And welcome to the WISH seminar of this week. Today, we are very delighted to have with us Dr. Avinash Nayak from Lawrence Berkeley National Laboratory. The title of his talk is Determination of Source Properties of Earthquakes and Extraction of Love Waves from Ambient Noise using DAS. Avinash Nayak is a postdoc at Lawrence Berkeley National Laboratory. His current research focuses on various applications of distributed acoustic sensing or DAS data in earthquake and ambient noise seismology. He obtained his PhD at University of California, Berkeley, working on seismic moment tensor inversion using 3D velocity models, source type characterization of small magnitude seismic events and hydrothermal tremors signals. Previously, he has worked on body wave tomography and surface wave tomography at a range of spatial scales as a postdoc at University of Wisconsin-Madison. Thanks, Avinash, again for accepting our invitation, and the floor is yours.
Okay, thanks a lot. Thanks for the generous introduction, and I'm really grateful for this opportunity to present some of our research at this seminar. So the title is Determination of Source Properties of Earthquakes and Extraction of Love Waves from Ambient Noise. So the talk is divided into two halves. One is looking at the source properties and one is looking at path properties. And both are passive applications of distributed acoustic sensing. So first, acknowledgements. So at LBL, I'm working as a part of a big team, the Imperial Valley Dark fiber team. And this project is really a team effort that involves people from Rice University, Lawrence Berkeley National Lab, Engineering, the Energy Science Division, Computational Research Division, ESNet, UC San Diego, Lawrence Livermore National Lab. This research is funded by Department of Energy, specifically Geothermal Technologies Office. So at the end, I will also present some data from the Sacramento DAS array, which was again assembled by people, both current or former people at Lawrence Berkeley Lab. And it was also funded by LBL DOE. Grants. So first, distributed acoustic sensing. Distributed acoustic sensing is pretty well established now. It's a technology that converts fiber optic cables used in telecommunication into massive linear arrays of axial strain rate sensors. So the technology involves a device which is called the interrogator. We hook it to a fiber optic cable. The interrogator shoots laser pulses into the fiber optic cable. Now, in the fiber optic cable, there are some impurities that are naturally present that scattered the laser pulses. And suppose we apply some strain to the fiber optic cable, and that changes the positions of these impurities. And because the position of the impurities changes, it also leads to a change in the phase of the backscatter light. Now, this phase change, because of change in position of the impurities, can be very precisely measured, and that can be converted into a measure of strain or strain rate. So there are many benefits of DAS. Low cost of cable, the data is wide bandwidth. We can get pretty high frequency data acquisition. Dense sampling, we can get measurements at every few meters, and long aperture, we can get data over lengths of tens of kilometers. So what is DAS actually measuring? The DAS is measuring axial strain or strain rate along the fiber optic cable averaged over a gauge length. So you can imagine this straight line is a fiber optic cable that is lying in the X direction. So displacement in the same direction can be ux. Its time rate or time derivative is ux dot. Then if you take the difference between the velocity at position L by 2 and velocity at position minus L by 2, this gives a measure of average strain rate over distance L. This distance is the gauge length. And the points where we get dash measurements, they're called channels. Now the channel spacing can be smaller than the gauge length. For example, in this cartoon, the red points are channels and L is a measure of the gauge length. So in this case, channel spacing is indeed finer than gauge length. But the measurements are not independent measurement. At each point, we are still getting a measure of axial strain rate averaged over the gauge length. So the next term is dark fiber. So dark fiber is cable that is already present and lying unused. So if we want to acquire seismic data, we can either install our own fiber optic cables. The cables are cheap, but digging a trench is expensive, or we can try to find fiber optic cables that are already present in the ground and nobody is using. So thankfully, there are a lot of fiber optic cables available as part of extensive telecommunication networks all over the world. So these two plots just show maps of fiber optic cables as part of telecom networks from just two sources. There are a lot more. So these fiber optic cables can be easily leveraged for seismological applications. And it only requires to hook the fiber optic cables onto the interrogator, which shoots the laser pulses and records the data. But not all dark fiber can be easily used for seismological applications. So the criteria are, it should be unused. The fiber optic cable should be buried in the subsurface. If it's hanging from a utility pole, it's not that useful for seismology. And ideally, it would not have like bad quality connections that would cause like optical loss as the light travels along the length of the cable. And to install fiber optic, to install interrogator and other infrastructure, we need some space. So there should be space available. So the first half of the presentation will show results from the Imperial Valley Dark Fiber project. The goal of the project is basin scale geothermal exploration and monitoring using surface fiber optics and DAS. So essentially it is, okay, we have DAS data in a geothermal environment. How can we use it to better monitor geothermal resources or find hidden resources? So as the name suggests, the study area is Imperial Valley. So this is the plot on the right is a tectonic map from Kasparov et al. So Imperial Valley is in Southern California, just north of US-Mexico border, which is this dashed line. It is at the transform boundary between North American plate and the Pacific plate. This cyan patch is a Salton Sea. It's at the southern end of San Andreas Fault, which is a strike slip right lateral fault. And south of the Imperial Valley, the transform motion is accommodated by the Imperial Fault, which is also a strike slip right lateral fault. Now there is a right step between the two major right lateral strike slip faults, and this leads to extension, crustal thinning, and very high heat flow in this area. So tectonically, this area is really active. There's a lot of seismicity, there are a lot of faults, and this area is also good for geothermal resources. So in this area, like north of US-Mexico border, there are 4 active geothermal power plants. There are 13 known geothermal resource areas, and USGS estimates there are a lot of hidden geothermal resources available. So what do we mean by hidden geothermal resources? It's geothermal resources that have no obvious surface expression, like hot water springs or fumaroles and like that. So many of the hidden geothermal resources were discovered accidentally. For example, you are drilling for oil and gas, but you find hot water instead. So this DAS project is giving us DAS data, seismic data. So what are we looking for in the seismic data for geothermal exploration and monitoring? We're looking for anomalous VPVS or VPVS ratio, seismic attenuation, faults, and earthquakes. So usually high fault density or high seismicity indicates permeability, which is good for geothermal production. We're also looking for coherent scattered waves that can indicate presence of faults or fractures. So there are other outcomes from this project. One is better understanding of seismic wave propagation, tectonics, and seismic hazard, because this is high quality, dense data acquired on a long aperture. So the plot on the left is a seismotectonic map of the Imperial Valley. The white squares are major cities: Calipatria, Brawley, Imperial, El Centro, and Plaster City. This black cyan line is a fiber optic cable that starts from Calipatria, goes south, and then turns west towards Plaster City. So on this fiber optic cable, we are acquiring DAS data on this segment between Calipatria and sort of Imperial, which is highlighted in black. This is a 27-kilometer segment. The dots on this map are a historical seismicity that color coded by depth. As you can see, there's a lot of seismicity. The major faults are San Andreas Fault, San Jacinto Fault Zone, Superstition Hills Fault, Superstition Mountains Fault, Imperial Fault. And between the San Andreas Fault and Imperial Fault, there is a very broad zone of distributed seismicity. Is called the Brawley seismic zone. So there are 4 producing geothermal fields that are highlighted by these purple polygons. This is the Sultan Sea, Heber, East Mesa, and Brawley geothermal field. So the DAS array we have goes very close to the Brawley geothermal field. So the plot on the right shows seismicity, like 7-8 months of seismicity during the period of our DAS acquisition. The triangles and squares are permanent seismic stations. We were also very lucky to record a big swarm in June 2021, which is shown by this dense cluster of earthquakes. There were more than 1,000 earthquakes in a week of time. So we were very fortunate to record this. So moving on. So these are some pictures and details of the DAS deployment and acquisition. So we are acquiring strain rate data on this array that is 27 kilometers in length. The channel spacing is 4 meters. So there are 6,900 channels, and the gauge length is 10 meters. So it's giving us actual strain rate averaged over 10 meters spacing. The sample rate is 500 hertz. And this system generates around half a terabyte of data a day. So these pictures show some hardware. The left plot is the HUD where the DAS integrator and other hardware is deployed. This is the second picture is a plot of the setup. There is a UPS to regulate electricity. There is a RAID server that stores the data. This device is the IDAS, and it's located on a vibration isolation table. I mean, any kind of vibration produces noise in the data. So we want to isolate the device itself as much as possible. And there is a temperature sensor to monitor temperature. So the long period noise is also sensitive to environmental conditions. So it's good to monitor temperature. So the plot on the figure on the right shows an example of a tap test. So now we have an idea of the geographical geometry of the fiber optic cable, but we don't know like which channel corresponds to which location. So what we do is we go to different locations along the fiber optic cable and then hit the ground with a hammer. And then in the data, see which channel is closest to the location where we hit the ground with the hammer. And this allows to map the channel numbers to geographical locations. So moving on. So I will show some example earthquake records. We recorded a lot of earthquake data. The 2 plots are for 2 different earthquakes. This is axial strain rate wave field. The first plot is for an earthquake in Westmoreland, is a magnitude 3, and the data and the distance was from the array was 8 to 21 kilometers. So if you remember, the array itself is 27 kilometers long. The bottom plot is for an earthquake near Ocotillo. It's magnitude 3.7, and the distance was 30 to 51 kilometers. The y-axis is time since the origin, and the x-axis shows both channel number and distance along the cable. So 0 to 27 kilometers. So thankfully, one of the permanent seismic stations is very close to the DAS array towards the end. So I took the seismogram from that seismic station and plotted on top of this record section. So which is this seismogram, CI-IMP. So one of the cool things about the DAS array is that because of the dense nature, it allows us to easily identify phases, especially scattered phases, that would not be obvious if we had only like 2 or 3 seismic stations. For example, the first plot, the waveforms are filtered in a lower frequency passband. You can see this secondary phase that arrives after the S wave. It's clearly some kind of like scattered phase. And so yeah, and if we had just one or two stations, it would not have been obvious. The bottom plot, the waveforms are filtered in like a higher frequency passband, and that sort of shows the P waves. So on this plot, the white points are P wave and S wave picks made from a semi-automatic way. The bottom plot shows the P wave picks more clearly, but at the channel where you have the seismogram from the seismic station on top of the record section, you can see the S wave and P wave arrival time match very well with the data from the seismometer. So we recorded a lot of earthquakes, and work is ongoing to pick P waves and S waves from as many earthquakes as possible. It's consuming. It's a very good S wave data set. Because even if you had a very long array, and if you're doing like active source study, explosions don't really excite S waves that efficiently. But with so many earthquakes, we can get very good S wave arrival times over this length of 27 kilometers. Unfortunately, this is a horizontal DAS array, so it measures horizontal strains. So it's not very good at recording P wave, direct P wave arrivals. Because P waves are supposed to be polarized in the vertical directions, because when they are vertically incident. So it does not record very strong P waves. I mean, these two earthquakes are kind of an exception. So we make P wave picks only at like short distances. So this is ongoing work. I will show some examples, some noise characteristics recorded by the DAS array. So in the top plot, I'm plotting a noise power spectral density as a function of distance along the cable. And it is color coded by the frequency passband. So blue colors are lower frequency, and warmer colors towards orange are higher frequency. So 0.04 to 45 hertz. So the fiber optic cables runs parallel to a railway track, and it crisscrosses many roads and few cities. So obviously there is a lot of like human induced noise, and you can see that based on the position along the cable. So the fiber optic cable starts from the city of Calipatria, so the noise levels are higher. As you go out from the city, the noise levels drop. So the section which is close to Brawley geothermal field is the quietest, where the noise levels are lowest, and that's because there is no major road close to it. But after that, we see a very strong peak in the noise, which corresponds to Highway 111. And then the cable goes through Brawley City, where again, noise is higher. What happens at further distance, as we go into greater distance away from the laser source, the noise levels start increasing with distance. And it's a very systematic increase. And the reason is, at greater distances, there are not enough photons or light which is coming back. There are absorption losses, and as you move further and further away, the strength of light goes down. So noise levels tend to increase as a function of distance. And because of the way the scattering works, noise levels also increase as a function of frequency. So you can see colors from like blue to orange. The noise levels are increasing with frequency and distance. And it's easy to confirm that a lot of the noise is human-induced noise. So in the bottom plot, I'm plotting noise power spectral density as a function of time over 1 week. The y-axis is frequency, and this data was from a section of the array in Raleigh, which is a city. So you can see the strongest noise is in the infrastructure passband, 1 to 20 hertz, and there is strong time variation in the noise levels. So you see like higher noise during the day, lower noise at night, and lower weekends. So we also were able to capture the secondary microseism peak, which is this section of high noise between 0.1 and 0.2 hertz. So now coming to like applications. So we want to see if DAS can be used to precisely determine earthquake source properties. I'll give some basic background. A very common way to model earthquake seismograms is think of it as a term, as a convolution of source term, a path term, and an instrument response term. So S is source, G is path, I is instrument response. So the source term captures source properties of the earthquakes. The path term captures the wave propagation effects and also the side effects in this case. And the I is instrument response function of the instrument that recorded the data. And this is a convolution in a time domain. So if you think of this in frequency domain, the convolution changes to a simple product of the 3 spectra. So what does this source term look like in time? So in this plot on the lower left corner, this source term, or in time domain, I will call it source time function, looks like a simple pulse. For bigger earthquakes, you can expect this pulse to have like longer durations. And for smaller earthquakes, you can expect this pulse to have shorter durations. So we like to work with it in frequency domain, and we like to fit a simple model to it. So one of the most common models used is Brun omega squared model in frequency domain. So when you take this source time function and take it to the frequency domain. So in this model, when you look at this in log scale, the spectral amplitudes are flat or constant at low frequencies. This flat level is directly proportional to the seismic moment. And beyond a corner frequency, the spectral amplitudes decay by 1 over frequency square. So both of these, seismic moment and corner frequency, are important parameters. So you may ask, like, why study this? Why is this important? So seismic moment is a direct measure of earthquake size. It's a static measure. It's a product of the slip, rupture area, and rigidity. The corner frequency is a very important parameter in hazard assessment and engineering seismology. And the reason is, the greater is the corner frequency, the greater is the amount of high frequency radiation. So it has a big impact on hazard estimates. And like from a source physics point of view, how this term corner frequency scales with earthquake size or seismic moment, it's a pretty important topic of research. So, so as you can see in this equation, let's say if you want to determine the source function, you can see that we need to correct for the path function and the instrument response function. Now, instrument response function is something that we know pretty well for seismometers, but this path term is very difficult to correct for. So we use an indirect approach called empirical Green's functions deconvolution method. And the idea behind this is, if you have 2 co-located earthquakes with the same focal mechanism, and such that the magnitudes are different, you can divide the spectra of the larger earthquake by spectra of the smaller earthquake. Now, if the earthquakes are co-located and they are recorded by the same instrument, then the path function and the instrument response function get cancelled. And we get a very precise estimate of relative source time function. And if there is good magnitude difference between the 2 earthquakes, then this source time function gives a pretty good estimate of the duration or the corner frequency of the larger earthquake. So So, I mean, our goals are very simple. We have a lot of earthquakes recorded by both DAS array and the seismometer data. And we want to apply this method to both data sets and see if we get the same results or not. So the data types for seismometers, the data are velocity data. The path functions are supposed to be for velocity wave field. The instrument response function for the seismometer. So, and for the DAS data, the data is strain rate. The path function are supposed to be for the strain rate wave field, and the instrument response is for the DAS. But the idea is when you apply this method, everything specific to strain rate or velocity or DAS or seismometer gets cancelled, and what you get are precise estimates of relative source time function. And the idea is to see if they are similar, and if not, why they are not similar. So we looked for earthquakes greater than magnitude 2, and we try to find similar earthquakes, co-located earthquakes, and it's pretty easy to find. I mean, the waveform should be as similar as possible. And for every pair of earthquakes, we apply a time domain deconvolution to both seismometers and DAS waveforms separately, and then compare the relative source time functions. So I will just show result for like one earthquake. So in this case, the top, for this pair of earthquake, the larger earthquake has magnitude 3.79. The smaller earthquake, I will call this larger earthquake master event. And the smaller earthquake has magnitude 2.18, and I will call it the EGF event. The first set of waveforms are for the seismometer data. The black waveforms are for the larger events. These are the two rows are for two different seismic stations, and these are 3-component seismometers. So there's east, west, north, south, and vertical component. The plot on the right shows the relative source time function, and from now on, I'll just call it the source time function. You can see the pulse duration is of like 0.4 seconds, and the numbers show distance. So this station was at 12 kilometers, and this is at 17 kilometers. So one of the nice things we can do is we can take the waveforms of the smaller earthquake, convolve this with this source time function, and see how the predicted waveforms of the larger earthquake will look like. In this case, the predicted waveforms are in red. You can see they are pretty close to each other. This is like 80-something% match. So this is a pretty good result. So the bottom plots are for the DAS array. So DAS array is 27 kilometers long, so it gives a lot of points of measurement, but not all points are good. Not all channels give good results. So it mostly depends on the signal to noise ratio for the smaller earthquake in the pair. So the larger earthquake generally has good signal to noise ratio. So these are similar plots. Again, the plots on the right shows the source time function, and DAS gives a lot of measurements. So these are 7 different numbers. They range from distance 17 to 31 kilometers. And they sort of look similar to what we get from seismometers, but not exactly same. If you look at the number VR, variance detection, this shows waveform fits, and it indicates the quality of results. As you can see, these numbers are lower. I mean, for seismometers, it was 85%, and this is like 45-something%. And there are 2 reasons for it. One is DAS data has stronger noise levels. The other reason is the strain wave field is much more complex than a simple displacement wave field. You can see the duration of shaking. It sort of goes on for a longer time, whereas the seismometer waveforms are pretty simple. So in this plot, I will compare source time functions from DAS data and seismometer data as a function of magnitude. So in each plot is for a separate earthquake pair, and the top of each plot I have mentioned the magnitude of the larger event and the magnitude of the smaller event. In each plot, the DAS source time functions are colored in gray, and the black curve is the DAS average. The green curves are source time functions for the 6 closest seismometers, and the red line is the seismometer average. So starting from top left corner to bottom right corner, the magnitude generally decreases. So it starts with 3.79, 3.52, 3, 2.9, and goes all the way down to magnitude 2. And I mean, unfortunately, the x-axes are all different. But if you look at the duration of this pulse, that also decreases from the top left to bottom right. So the top left plot, the duration is like 0.4 seconds. In the bottom right, the duration is 0.05 seconds. So yeah, if you look at these plots carefully, so in most cases, the seismometer average looks very close to the DAS average, both in terms of like the relative amplitudes and both in terms of like the duration of the pulse. We run into problems at lower magnitudes. So in this data set, like in our analysis, the lowest magnitude for master event is magnitude 2, and the EGF event magnitude is 1.3. So if you look at the seismometer median, which is this red line, it's much more sharper than the DAS median. And the reason is for smaller earthquakes, particularly this EGF event magnitude 1.29, the noise levels in the DAS data at high frequencies are significantly higher. So the signal to noise ratio is really bad. And therefore, the method causes the source time function to be smooth because it cannot fit the high frequencies in a systematic way because that's just noise. So it's sort of, the method sort of forces the source time function to be smooth so that the high frequencies are filtered out and the fits look good. So generally our results look good for master event magnitude 4 to like 2.4. So our DAS array also recorded possible observations of directivity. So for an earthquake on a fault, the rupture usually starts from the hypocenter. And if the rupture spreads uniformly in all directions, we should expect the same source time function as a function of like azimuth. Now, if there is a preferential direction for the rupture, so for example, in this cartoon, this black line is a fault, and there is rupture that is progressing towards the right. So in this case, we would see like a systematic variation in source time functions. So if the rupture is moving towards you, we'll see a sharper pulse, and if the rupture is moving away from you, we'll see a broader pulse. And the frequency content will be different, but the area under this source time function, which is the scalar seismic moment, that should be the same. So one of the benefits of the DAS array, because it's pretty long aperture, 27 kilometers. So if you have earthquake very close to it, it gives observations over a big azimuth range. So in these two plots, I'm plotting source time functions for two pairs of earthquakes that were very close to the DAS array, within like 1 or 2 kilometers. The left plot is for an earthquake in Southwest Brawley, and the right plot is for Southeast Brawley. And the master event is pretty small, 2.03, and EGF event is 1.2 or 1.3. So in these plots, the source time functions are from the DAS array, and they are color coded by azimuth. So you can see these observations cover a 150-degree range in azimuth. And it's not that clear for the second earthquake, but the first earthquake clearly shows that there is very systematic change in source time functions as a function of azimuth. If you look at the blue color and the brown color, the source time functions towards the north clearly have like two separate pulses, and the source time functions towards the south have like a single broader pulse. So we feel that this could be a possible observation of directivity, even for an earthquake that is small, magnitude 2, directivity or more complicated rupture. So we are doing a bunch of synthetic tests to confirm whether this could be possible by earthquake mislocation or things like that. So I mentioned previously, we are very fortunate to record a swarm in June 2021. And that swarm produced examples of clipping in DAS data. So there were many earthquakes of magnitude 4 and 5. So one important, and this is important if you want to use DAS data to record strong ground motions. So one important thing to remember is DAS data records space, the phase of the backscattered light. And that phase would be in the range of -pi to +pi. If it's greater than pi, it would wrap around. So this is what sort of which causes the clipping. In this plot, I'm showing DAS records of earthquakes at a range of distances. So different columns are for different channels, and they are increasing in distance from the earthquake. So this is channel 350, average 11 kilometer, then 12 kilometer, then 14, then 16, then 23. Different rows are for different magnitudes, and the magnitude decrease from top to bottom. So this number, like top left corner of each plot, is the magnitude. So 5.2, 4.1, down to 1.6. And for this plot, we have converted the raw DAS data to phase. So you can see that all numbers, all values are between plus minus 3.14, which is pi. The red numbers at the bottom right corner of each plot are the peak values. So the largest earthquake in the swarm was a magnitude 5.2, and you can see it got clipped at all distances. The earthquakes that were magnitude 3.6 and 4.1, so earthquakes in the magnitude 3 and 4 show like variable clipping based on the distance. Generally, for this swarm, at these distances, earthquakes that are lower than magnitude 3 are recorded on scale. In this plot, the smaller earthquake of magnitude 1.6 is only recorded at the closest channel. I mean, it is below the noise floor at greater distances. Another cool thing you can just obviously see in this plot, at the channel which is towards the end of the DAS array, the noise level itself is much greater channels closer to the interrogator. You can see that in the last column, the noise levels look obviously higher. So this is sort of like my conclusion from the first half of the talk. So the DAS dynamic range and bandwidth are sufficient to extract relative source time functions for magnitude 2.4 to 3.9 earthquakes in Imperial Valley, with the corresponding empirical Green's function earthquakes around being 0.7 to 1 magnitude unit lower. And time domain deconvolution method suffers from poor signal to noise ratio of DAS records for smaller magnitude earthquakes. So the EGF event would be lower than magnitude 1.4, which leads to loss of higher frequencies and smooth nature of source time function. And this would also be obvious if we are using a frequency domain deconvolution method. So how are we doing that time? Okay. So I will go through this like pretty quickly. The second part of talk is on ambient noise cross correlations. And the idea is noise cross correlation of diffused wave fields. And it could be ambient noise or coda waves recorded at pairs of two sensors converges to the empirical Green's functions. So if I have two sensors and record noise over long periods of time, it gives us a response to a medium of the medium to a virtual source. And this has caused, this has been very helpful in our field because our noise sources are at the surface. So doing these cross correlations give us the surface waves, and that can be used for surface wave tomography. So typically, like multi-component noise cross correlations are useful. If we have two seismometers, we can sort of rotate them in the radial, transverse, and vertical direction, and cross correlating two pairs of component, the three components for each seismometer give us a 9-component tensor. And the radial vertical components have Rayleigh waves and Love waves on the transverse components. So, I mean, DAS data has been used for surface wave imaging a lot, but there are problems. One of the problems is there is only one component of strain. It only records axial or radial strain. So if you have a straight segment of fiber like this, then you're cross-correlating radial noise with radial noise and it gives Rayleigh waves. But it's problematic when you try to cross-correlate two segments of cable that are in different directions or that are not in a straight line, then typically you get a mixture of Rayleigh and Love waves, which is pretty difficult to interpret. So what we are proposing here is correlating seismometers, 3-component seismometers with DAS, and that is useful in many scenarios. For example, if you have a DAS array, then it's possible there are some permanent seismic stations close by, or you can sort of deploy 3-component seismometers yourself, like a temporary network. And the idea is pretty simple. So the basic equation of noise cross correlation is this. So you have ith component of velocity at position A cross correlated with jth component of velocity with at position B. And this gives me the displacement response for displacement in ith direction to force apply in, displacement response in jth direction to a force apply in the ith direction. This is the Green's function. So what we can do it instead of jth direction of velocity or the jth direction of the Green's function at the receiver, I can take a random direction x and take a spatial derivative in that direction. So now we can interpret this equation as velocity noise at position A cross correlated with axial strain rate noise at position B gives an axial strain rate response, Green's function response. And this is useful because even though DAS is one component, we can cross correlate seismometers with the DAS data. And the seismometer components can be rotated to the transverse, radial, and vertical direction. Now, if the Earth is very close to a 1D and isotropic medium, the radial force and vertical force will preferentially excite Rayleigh waves, and the tangential force will preferentially excite Love waves. And that's how we can get Love waves out of DAS data. And this is very useful. So in the following slides, I will term components of seismometer DAS noise cross correlations as TX, RX, and ZX. So T, R, Z are the 3 components of the seismometer that are rotated in the transverse, radial, and vertical direction. And X is the component of the DAS array in any direction, whichever direction the fiber optic cable is going. So I'll skip these slides in interest of time, and I will directly show some real data. So we also acquired DAS array data on a fiber optic cable near Sacramento in Northern California. These, for location reference, the city of San Francisco would be roughly to the south west corner. These triangles and squares are permanent seismic stations. So black triangles are broadbands, squares are accelerometers. This black line is the DAS array. And this plot on the right shows an expanded view of the DAS array. It's around 22 kilometers in length. It starts from West Sacramento and runs till Woodland. So as part of the experiment, we also deployed a broadband seismometer close to the DAS array. So the idea is to cross correlate the noise from these permanent seismometers with the DAS array and also this temporary broadband seismometer and compare the results. So in each of these plots, the waveforms are noise cross correlations for a single seismic station acting as a virtual source. So in each of these plots, the gray waveforms are seismometer DAS noise cross correlations, and the red waveforms are seismometer cross correlations for that one seismometer that was close to the DAS array. And the top plots compare TX and TD components. The bottom plots compare ZR, RR, ZX, and RX components. So the top 4 plots show examples of Love waves, and the bottom 4 plots show examples of Rayleigh waves. And this is distance ranging from all the way from 0 to 80 kilometers. So as you can see, we see very coherent surface waves with very systematic move out. Comparing the gray waveforms and the red waveforms, we see generally the arrival time is similar, and even the relative amplitudes on the causal and anti-causal sides are also similar. So we can also go one step ahead, and for the DAS channel that is closest to the broadband, temporary broadband sensor, we can measure the dispersion curves. So we measure dispersion curves using the automatic frequency time analysis method. It required some modification because the method is mostly for displacement data, but we modified it to measure for strain data. So in each of these plots, we showed dispersion curve for the noise cross correlation of the DAS array and one channel of DAS array and the seismometer close to it with one virtual seismic source station. So the larger numbers are phase velocity measurements, the smaller numbers are group velocity measurements. The black symbols are for the DAS noise cross correlations, and the bottom symbols are for the seismometer. The red symbols are for the seismometer noise cross correlation. The first 6 plots are love waves. The bottom 3 plots are Rayleigh waves. So we see a very good match between the phase velocity and group velocity dispersion measurements, both for love waves and Rayleigh waves over the frequency range. So conclusions for this is, so the combination of inertial seismometers and DAS arrays is very useful. So if you have like a well-distributed permanent or temporary network of seismometers around a DAS array, it is possible to do 3D surface wave tomography. And using cross-correlating DAS data with 3-component seismometer data, like doing noise cross correlations, we can also extract love waves. And another important result is, since seismometers have generally lower noise levels than DAS, we can expect to recover seismometer DAS noise cross correlations at larger distance. So then it's possible with just DAS noise cross correlations. So in this case, we were able to recover noise cross correlations at 80 kilometer distance in the secondary microseism passband. So towards surface wave tomography using DAS seismometer noise cross correlation. So as part of this project, we recently deployed, so again, this is going back to the Imperial Valley DAS array. We recently deployed around 69 3-component 5 Hz nodal seismometers. We also have like 3 broadband seismometers that are in the area. And this is equipment that is borrowed from Pascal. So all the data, the seismometer data will be available. So this is like ongoing work. So yeah, thanks.
Thank you very much, Avinash, for this very interesting talk. And if you have any questions for Avinash, please unmute yourself and just speak up.
I think so. You okay? Okay, I can
Can you hear me now?
Yep.
Thanks for the talk. So you mentioned on one of your slides during the swarm, the 2021 swarm in June, that the DAS data was clipped.
Yes.
And wondering if you know if there are any acquisition parameters, like maybe the laser pulse wavelength or something that can be adjusted to guarantee that, you know, earthquakes below, you know, ground motion below a certain magnitude will be unclipped. Is there anything that you can do?
Yeah, the clipping level depends on a number of parameters. One, as you mentioned, is the wavelength. The other one is gauge length. The other one, another parameter is sample rate. all these parameters can be varied to get the clip level, but it also depends on like it will also, all these parameters, changing all these parameters will also modify the data quality. Like if you lower gauge length, then the data quality becomes worse. So it's sort of like a trade-off. But you're right. I mean, there are many parameters that can be varied to change the clipping level.
And do people have kind of like rules of thumb for how to pick those parameters, or is it a bit of an art still?
I mean, when we I think when we started, we did not really think about this from the point of view of clipping. So we sort of used parameters that were sort of like general parameters, I think. And so, but like now having observed this, so yeah, I mean, it's advisable that if you're in an area with a lot of seismicity, then maybe set these parameters to sort of make sure the data would not be clipped. Yeah. Generally, I mean, there is a mathematical expression that relates the amplitude of the data to all these parameters, and so you can sort of vary these parameters and see how the strain level or the phase will change, and decide accordingly.
Okay, so that result does exist.
Yeah, there's a formula that exists.
Any other questions? Oh, yeah.
I ask a question?
Yeah, go ahead, please.
Yeah, thanks for the nice talk. It's very informative. I have several questions regarding first the source part, the signal recording, and also the Love-wave tomography part. First off, I think there might be a mismark on the microseismic part on the spectrum of the dark dust signal. Can we go back to the slide?
Yeah, sure. Let me know when to stop.
Yeah. Still.
This one or?
At the beginning, I guess. Pretty much in the beginning.
So I think.
Oh yeah, here. Oh. Is there any? Am I frozen? The last slide you showed, the spectrum of the dust signal, the colorful spectrum.
Oh, this one.
Yeah, exactly.
The noise level,
yeah. Yeah. I believe that the blue part, the first part is the secondary microseismic should be the one in the middle, and the part you marked should be the primary.
So you mean like this point?
Yeah.
I thought this was between like 0.1 and 0.2. So this band, like this peak.
Yeah, it seems to me like this is a more than 10 seconds, right? It should be the primary. Yeah.
So this.
But I think in the middle it should be the secondary.
So where do you want secondary to be, like?
Yeah, this part.
Well, this would be like one hertz or so.
Beneath 1 hertz.
So
between 10 seconds and 1 second. That should be the secondary microseismic.
Yeah, so yeah. I mean, I just put the text slightly lower so that I don't put it.
Okay. I'm sorry. Yeah, this is a misunderstanding. Yeah. Another thing is about the source time function. I wonder, how did you determine the red edge of the birth of the source time function you got from the spectral ratio?
So sorry, can you repeat again? Determine what? Like the.
I wonder how you get, yeah, exactly this figure, how you estimated the age of the source time function, the edge.
So, I mean, it's mostly right now, I don't have like sort of formal estimates of the edge of the source time function. And a very common way to do it is calculate sort of an energy level, so squared of the amplitude, and you can pick the edge where it exceeds 5% level, and the other edge would be where it exceeds 95% level. So like 5 to 95%. In this case, the data are pretty well behaved. So the red tick marks look very nice, but I can guarantee you in vast majority of the cases, it look pretty bad. So, I mean, so far, I have not figured out a way to automatically calculate the edge, sort of the two edges of the source time function. So yeah, I mean, this is just like a good example. It doesn't work in most of the cases, mostly because for smaller earthquakes, the source time functions don't look as nice as this.
And when we get the source time function, you convolve the EGF event with the source time function. Shouldn't we get always the same waveform if we, because the source time function is getting from the EGF method, no?
Yes, yeah, well, so the inversion I'm using is a time domain inversion method, and it's a damped and smooth least square inversion method. So based on the damping and smoothing parameter, the source time function won't exactly give you the actual waveform. So yeah, so that's why there is a difference. I mean, if the data is really good, for example, this seismometer data, the fits are like 85%, but for the DAS data, which have very high noise levels, the fits are low, like 45%, and that the difference in fit is essentially coming from the damping and smoothing parameter that is applied to the.
I think based on the difference between the black one and the red one, it could be a good method to determine if we picked the right part of the source time function.
Yeah, I agree with that. I agree with that. Yeah, I mean, there are a lot of like finer things about this, and a lot of things can be varied. You're right, you're absolutely right.
And the last one is, I wonder what frequency range you will use for the Love-wave tomography using DAS data.
Oh, so that's a pretty good question. So, I mean, so again, go back to that map. So in this case, I mean, if you look at the distances over where we calculated noise cross correlations, these stations in this plot are like, many of these stations are like 70-80 kilometers from the DAS array. And in the thing is, the noise level in the secondary microseism passband, 0.1 to 0.0 hertz, is like so high that we can get good noise cross correlation even at to like 150 kilometer distance. The problem with this area is that there are not a lot of stations like close to the DAS array. So it doesn't really let us take advantage of the dense nature of the DAS array. And that is one of the reasons we just are trying to get data from like this temporary seismic network, for which the distances are like much closer to the DAS array. So in that case, the data was mostly like 0.1 to 0.3 hertz. And I expect for this, we can go to like 0.1 to 0.5 hertz. And for the closest station, maybe to like 1 hertz. So it is mostly like a distance thing, but we'll have to see. We haven't seen the data yet. So
I see.
Yeah, I mean, I guess like it would be, I mean, theoretically there is not, I mean, I don't see anything wrong with the method, except if like the Earth is like really 3D or strongly anisotropic, then we cannot like separate love waves, Rayleigh waves that easily. But I mean, at the end of the day, I think it should be what frequencies is the DAS data or the seismometer data sensitive to. I think if it's recording that noise, it should give something back in the noise cross correlations. So that is the idea. I'm not sure if it will work or not. So
very interesting. Thank you very much.
Yeah,
thank you.
Yeah, thanks for the questions.
Any other questions for Avinash?
Hello, this is Rachel Abercrombie.
Oh, hi.
Hi, officially at Boston University, but I spent a fair bit of time at MIT. I really enjoyed your talk, thank you. And I was fascinated to see what's possible for the source analysis. I haven't seen source analysis like this coming out of DAS data before. So I'm very interested. If I can be of any assistance, then send me an email and I'd be very happy to talk to you about ways you can measure and things like that.
Yeah, I mean, this is still a work in progress. So yeah, I will definitely contact you.
Okay, I'll look forward to hearing from you. Thank you very much.
Any other questions? Yeah, if no further questions for Avinash, let's thank him again for this great talk. Thank you.
Thanks. Yeah, thanks for giving me this opportunity. I really appreciate it.
Thank you. And Josh has ordered lunch box at the second floor. So we will see you in the next week. Thank you, everyone. Bye-bye.
Thanks.
Thank you.
Bye.